Welcome everyone to this lecture. I think you should be able to hear me this time. And I've learned from my mistakes and I didn't forget to click the always on top check button for the chat window this time. So without further ado, I think that means I've seen that you can hear me. So we can get started. And this is I think, we already kind of did a little bit of this in the last week, but here we really get into the meat of the course. I'm going to show you this week how we can start to break things. There have been a bunch of questions about the magic function exercise that you were asked to do, the one where you needed to figure out how much stack space something uses. I will get to that at the end of the lecture. Hopefully I can get my tablet online and draw some pictures there as well. But there are some hints that I will give you at the end of this lecture. Then, of course, my slides. Yeah. Okay, so what did we do last week? We talked about the different segments that programs are partitioned in. For example, the text segment where program code are, and data and BSS that contain global and static variables. And all of these start from the low addresses, so from 0000, usually not exactly there because there's reasons to move it around in memory, but at the low addresses you can find these segments. Then at the stack, at the high addresses you will find a stack. That starts from the very top, at least the very top of user space, and then grows downwards. Recognizing the stack also really the best thing you can do there is, does it start with 7FFF? It's probably a stack variable. The stack contains return addresses, function point arguments, frame pointers, and more importantly, all of the local variables. And it's automatically managed. We went into that in great detail last week. I showed that the only thing you need to manage the stack is the stack pointer, and just by incrementing and decrementing it, you can get the behavior that you want for local variables. Of course, if you keep only track of one thing, it's kind of hard to see when you start overriding other things, and that's what happens when you overflow the stack. It exceeds the maximum size, and it often happens when you're having recursion. The heap is the other side of the memory equation in C, and that is where you can park persistent or large data. You can get a segment of the heap using malloc. You can resize it if you want. But in all of these cases, you always need to check if the return pointer is null, even though that might seem exceedingly unlikely. If you have successfully allocated memory, then you can free it. Of course, if allocation failed, you shouldn't free it. But this all means that you as a programmer need to be really careful about how you manage all of this memory, because you need to be both careful that you don't free it twice. You need to check if it's successfully been allocated. You need to think about how much size do I need, etc. The heap is really a bit of a hassle in that aspect, but also powerful, and also indeed the only way you can get new slices of memory that you can pass up the stack instead of just down the stack. Yeah, so programmer managing memory means programmer screws up memory, double free, use after free, memory leaks, pointers that point to freed memory. Well, then you get a use after free eventually. This is the kind of thing that goes wrong, and these are all links to CVE lists that found. These are all vulnerabilities that see that even in 2020, these kinds of issues still happen a lot. Slides. If you want to get zeroed out memory, then you can use calloc. Otherwise, you're liable to find random other stuff in memory that you've just allocated. Non-initialized memory, reading that, of course, is undefined behavior, but yeah, it is technically possible, but then you will usually find garbage. As a brief reminder, I will go again into using function arguments. You might have seen that you've called programs like ls or something with arguments, and they're passed to the main function in argc, argv, where argc is the number and argv is an array of character pointers. Argv0 is always the name of the program, and then you will find the arguments that follow after that. Okay, so everything in a program is in memory. My slides are being a bit slow, and that is being annoying. Yes. Why is that? This is the von Neumann architecture. That's a picture that they made, Mr. von Neumann made a long while ago. You might have seen this picture before in a book on operating systems or introduction course somewhere. And basically the idea here is that you can model all sorts of computers as this picture. You have an input device, and then there's an output device, so say your keyboard or the internet or whatever. And there's an output device, namely your screen or a sound card or whatever. And then there's this processing unit that talks with this memory unit. And the magic happens. There's this control unit that makes sure that your data flows as you want it. The arithmetic unit makes sure that 1 + 1 works. But basically something comes in, something happens, something goes out. What you might see here is that there's no special treatment between program code and program data. So all of the things that this control unit is doing are influenced by what is in the memory. And in practice, we also see that, we saw that last week when we saw that return addresses, which are definitely control information, are stored in between the information that you want to do arithmetic or logic on. This makes, similarly, the source code for your program is also in your memory space of your process. So you're not just doing this memory bookkeeping with malloc, etc. That's not only for data, but usually in the background. That same thing is being done for the memory that's allocated for the source code of your program, etc. And this is problematic. So if we know that the programs are controlled by what is in the same memory as the variables that we are reading and writing, and we know that C does not check what we are doing to the memory that we are reading and writing, and if that makes sense or if that's malicious or not, this should more or less be your intuition by now. Of course, we've seen these sorts of slides before. Memory safety means security bugs. If there's no memory safety, then you can quickly get all sorts of vulnerabilities, etc. This was a picture last year. 70% of all security bugs are memory safety issues. And here memory safety again means stuff like malloc failures, use after free, stack overflow, buffer overflow, etc. And this was 70% of all vulnerabilities in Microsoft products. And I think that they usually have the skills and the engineers to make sure that they test their stuff. I have no idea what this figure is for more general software development. So what we will be doing in the next weeks, we'll be reading data from memory that we shouldn't be able to see. We also already kind of did that last week. we'll be going to get a program to call functions that it shouldn't be calling. That's something you're already going to be doing in the homework. We're going to inject our own code into a program. So we're going to trick a program into executing code that is not part of the C code at all. So there might be a program that just does a memcopy and a printf, and that's all it does. And we can make that program launch a shell. And that is all sorts of commands that we're going to be calling that are not part of the code of that program at all. And we're just going to add that to the program while it is running. And what we're also going to be doing in the next week is hacking into a remote machine. We've talked about that before. The exam is going to be a bunch of that kind of exercises in various levels. I'm still working on both a platform where you can start up exercises and then hack them and then submit a write-up, and then I can collect all of the information that you did in one go. I'm also still working on the actual exercises, as in things that you need to hack. But I imagine that all of you are quite curious of what the exam is going to look like. There will be a website. That website will have different challenges, more or less, and the idea with that you can do a challenge, do the kind of exercise that it describes. So, for example, you need to figure out if a certain variable value of, or trick it into launching a different function or something. I might also have such exercise at different levels. So one that's more easy because it gives you a lot of help information. Another one where you might need to extract that information yourself from the program by giving it the right input. And then I want you to write a bit about how you broke the program, what you figured out, or if it didn't work, then you can still submit something. Okay, I learned this and this and this, and I think I need to do this, but I couldn't figure it out, etc. So much like the homework exercises. And then I will grade you not so much on the actual I've broken something count, but on the write-ups. So if you demonstrate enough skill, but it doesn't work because something is being stupid and there's some minor detail that you just can't figure out, then you should still be able to write a sufficient write-up of that attack, and thus perhaps still get a passing grade. I hope to already have this platform soon, as in that you can already practice with it for a homework exercise before you're supposed to do an exam. And that would also be an excellent opportunity for me to get feedback and test everything, and for you to get experience with it and get help from the student assistants while you still can. So yeah, printf. We saw printf again last week. It takes a format string, and that is format string specified how subsequent arguments are converted for output. You have all of these formatting characters. Remember that there's these prefixes for example, the D command, where you have L that instead of an int uses a long int, or H for short int. If you use HH, you can print a character. There's also these things that you might not have seen in this form before. That's this is a 0, and then there's this number n, and this you can use to print a hexadecimal integer that's at least n characters wide. So if you want to print an 8-byte address, then you need 16 hex chars, but the first bytes, for example, might be 0, but you still want to see them, then you could do %0 16 x, and then you will get 000 blah 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 x. There's also this special syntax that will print the nth argument of printf as a hexadecimal integer, and you can also combine these things. I think you can do %n, so then, for example, 7, then a $sign, and then 016 x to then print it as a the 7th argument with 16 characters. Yeah. So we saw this last week. What does this program do wrong? Well, this should have been a printf with %s here. And if you give this program %s here, and if you supply it with an argument that is a format string, such as this one, then you will start printing the arguments. You'll of course start printing with the second argument first. And remember that the first 6 arguments of a function were passed on this in registers, so you might need to pass a bunch of %x's before you start reading memory. Yes, back to this. This x here is just a placeholder. You can use that with any one of these things, except %p doesn't really like this format, but the rest you can use this 0 filling and the number of arguments with any of these formatting characters. So what do we see again? If you run printf with some formatting string, then we will start to see things. So I have here printf.c, which does a printf here, and make printf. Then you'll see that you print an address. I could also do 016. And then you'll see that it starts to 0 fill this, accident, 0 fill this address. You might, by the way, notice that it's different every time. That's because I'm using address. Your computer is randomizing these addresses each time a program is run. We'll get to that again. But you might need to, there's ways to turn that off. So if I call set r -r or disable address layout randomization, and then call printf again, then we should see that it prints the same thing every time. My shell that I was using with the pretty arrows, etc., if there's no end of line character, it will print this % symbol and then a new line. That's why you were seeing that. That was not actually part of the formatting string or anything. But that does mean that, like here, you get these annoying behavior where there's not a proper new line, so you get this thing on one line. The shell, if you want to steal that, it's called Powerline. If you Google Powerline shell, you can find, I think, soon enough what this is. So yeah, there's also this $$ syntax. So $7. Then you'll apparently that's a null. Oh wait, you always need to be careful with the $ signs, because a dollar is also the variables in the shell. So example, the path variable. This variable controls all of the different places where executables can be found, such as Perl programs, Java, more Java. Things are slightly duplicated. Use a local bin. I use Ccache, etc. That's a list of directories where it will try to find executables. And here, if I use this without quotes, without single quotes specifically, then it will start to read here $p, and that's simply an undefined variable. So let's use single quotes here, and then you'll see that this was the first thing that was on the stack. So I could also do 8. You'll see that there's another stack variable, and this thing might indeed be a return address, because it's somewhere higher. Back to the slides. Yeah, if you want to read something as 8 bytes 0 padded, I forgot, if you should also use this L here to print it properly with, because then you want to read 8 bytes, which is why you need LX and then 016 to pad it. These addresses are randomized. ASLR means address space layout randomization. That's a thing that will move around everything in the memory slightly with a random offset every time. And the reason for that is that it makes attacks a lot harder, because whereas if I just have this program, yeah, you didn't see that, but I accidentally clicked away my window. And I print this thing. Let me go back here. So the 9th one was the return address. You'll see that it's slightly different each time. It's still somewhere in the vicinity of the top of the stack, but you'll see that there's some randomized offset. The lower part is more or less the same every time, but the upper part is a bit weird. It moves around quite a bit. That makes it harder to break this, because I would have to both learn what an address. So say I want to overwrite, put this address that I learned and use that somewhere else to do an attack. Then I would have to, if I don't have this layout randomization, I can learn the address first and then just use it from then on. Whereas, so I would have to only have a vulnerability that I can use to read something with, and I will also need a vulnerability with which I can write something, but that can be the same vulnerability, and I don't need to do both at the same time. As long as that I have a vulnerability that allows me to first read something, and I can use that same vulnerability, write something, I can execute an attack. But if this address is different every time, then I would have to both read the value that I need and write that same value during a single execution of the program, because the next time I'll run it, the address will be in a different place again. Useful defense against the basic attacks. There's a way around it, of course, but for us it's a lot easier to just turn it off. So let's do that again. Set r minus r. I want a proper shell. There. So that was Aslar. So we also saw this example last week, where if I that was the one that I just had in my terminal, where if I start passing in a lot of printfs, I'll actually just use bash, because then I don't have a lot of garbage. With the larger font size, it's a bit harder to read. So printf hello world is all fine, but I could also do printf Perl execute print %p, and let's get 30 of you. Actually, let me add a space here, and actually let's print it slightly nicer. So %0.16 lx and a space, and then you can see that I can nicely print all of the variables and read the addresses with the 2 leading null bytes, because addresses are 6 bytes, but they fit in 8 bytes. There's a little bit of null space here because that never does everything align nicely. Some address here. And here was the variable that we saw defined in the source code. So again, let's look at the source code. There was this function in the stack frame above where printf is, doPrint is. So if we just start dumping parts of the stack, you'll see here some value. Here's another return, possibly other return address. Yeah, we can. Yeah, let me go back to my slides. Yeah, so if we start doing this kind of thing. This is an inline Perl program. That is the way that I use this, but you can also just write 14 times RP. Then you can start reading things, and you'll see that we found the return address here. This is just a reading up the stack, but we might also use this printf bug to read anywhere. If we could just read up the stack, this attack would not be as powerful as it is. Typically, the string being input is somewhere on the stack. So if we assume that this string is above where we're reading, then we can use it. And if we also then remember the %s formatting character, this formatting character gets the argument that it's in that position that it is currently reading, but then it doesn't read that as an integer, which is just a straight translation of bytes. It reads this as a character pointer. So it looks at that address, follows it, and then reads the string that is at that address. So if we can put an address in a place where printf will read the argument from, we can control where printf actually reads. I also had an example for this. So we have, yes, clear. I had to look at my notes for a second. So printf of stack, let's see. We have this program. It is, let me actually print it nicer. There is this program printf buff stack. It takes some arguments. We have this buffer that is quite big. We zero initialize it. And we have this buffer for the secret. And we copy to the buffer my secret string. The reason that we're copying it here instead of just assigning it is because otherwise we'll get a pointer to something that is not on the stack. And for this example, it's nicer if we're just printing something from the stack. So if we want to attack this thing, I can just do Perl -e print %016 LX. Let's do 30 of you guys. Closing. This printf, but I also need, this was the old program. Printf of stack. You can see that we have a bunch of things here in the memory, zeros, some other stuff, and there appears to be something here. Actually, let's just go look at what this is. So I'm copying all of these bytes, then I'm going on the internet, and then I'm going to look at this. This is just some hex to string calculator. I'm going to click convert. Interesting. What is this here? Percent XL601. Wait, that seriously resembles having the percent O16LX. And in fact, that is what we're reading there. This is the input that we gave to program. But why is it in this weird order? Well, that is because of endianness. Remember that in every 8 bytes, then it's stored in a little endian form. So the first byte is at the end, and then it's swapped like that. But then per 8 bytes. So if we start to convert this, then we have, I would need to split this into blocks of 8 and then start to reverse it. This also reveals that there is this string here, which consists of these letters, but it's slightly hard to figure out what exactly this is. So let's just try to figure something out. There is, let me add a space here. This looks like an address. 1, 2, 3, 4, 5, 6, 7, 8. Now let's print a bit more. 50. This is still all the inputs. What was my notes again? Oh yeah. We can see that that doesn't really help us. Oh, am I being an idiot again? Yeah, I am being an idiot again. Sorry. Yeah, so if I just start printing more, we'll see that I'm just getting more and more of my formatting string because it's a bit big. Fortunately, I clicked outside of my terminal window, so it disappeared. I have this secret again. If I want to now, I know where this thing is, so I can try to print it. My notes say that this should work, but I need to reconstruct why that is again. No, that's not correct. You shouldn't make notes and then change your program, Tom. Makes it very hard to attack it again. Let's roll back a bit. We have this address where the secret is, and we want to print it. We've already seen that the thing is on the stack, and we can try to access it, but we can also spoilers, stupid. Oh, this is amazing. Okay. So apparently OBS recognizes the windows solely by the title of the window. So I had selected that it would do this terminal window as the thing it should display in OBS, and then I secretly tried to open a second one so I could look at my notes. But what just happened is that OBS switched to the new window because it has the same title, namely terminal. And that is a bit annoying. This is the downside of all of this software usage. It's not always as convenient as I would have done in a normal lecture. Yeah, so where were we? Make printf buff. Yeah, let's look at this example instead. So let's print this with syntax highlighting. Here I have a nice global variable called secret. So this is not on the stack. So if I want to print that, I either need to print gazillion %ps, which will probably not be allowed because I'll go over the stack and start to crash things, or I will need to be smarter. And let's try to be smarter. So what I can do is I can use, if I make printf buff, I've just done that, then I can start printing things. And yeah, it's nice and blinky. And why is that? I've included some magic characters here. This one means please blink for me. This one means please turn it red. And this one turns off all of the special coloring again. So this is why we get this nice blinky output. Let's go back to my Perl program. Perl print %p times 30 or 40, whatever. Should use the correct quotes here. Close the Perl program, and I need to use -e. And you'll see that there's a bunch of this stuff, and yeah, you see here, this is the %ps, because percent is 70, p is 70, percent 25, and the space is hex 20. There are these other things, some of the things that were in the registers, some address, but this pointer is nowhere to be found on the stack. And that makes sense because we didn't have it as a local variable. It was a global variable that you used. Printf buff.c. So if you want to print out what is the value of secret, we can need to do some magic. Namely, we need to insert it into the memory. Inserting it into the memory is slightly difficult because you need to make sure that you have overwrite the address correctly. And what does that mean? Well, we need to make sure that we overwrite it with the null bytes. Remember that an address is 6 bytes long, and but it fits in 8 bytes. So that means that there's 2 bytes that are null. And where is my? Yeah, I have a small helper program somewhere called reverse. This is not part of the instruction, but just something to get my thing working correctly. Yes. stupid. I have this helper program that allows me to print a address not only as nice characters, because remember we're getting the where did I have that? We're getting the hexadecimal representation here, but we need to print it if we want to overwrite it with the not with the digits, because this is a string of digits that happens to be the hexadecimal representation of this address, but we need to overwrite it with the bytes that this number represents. So if I do use my small helper program, I will give that program to you once it becomes relevant. It will dump that as the bytes in little endian order. So you'll see that it's more or less reversed, not exactly reversed, but it's now in little endian order. And I've dumped it through XXD, which is a Hexdump program. So it shows that starting from 000, this input, we have these bytes if we represent it in hex, but these bytes don't necessarily have a printable version. So 55 apparently is U hexadecimal, the capital letter U, but AT is not a printable character, which is why it is this dot. The thing here is that I can start to try to insert this into the program. If I do bin reverse then we can start to see that I have so let's do that. That here we have again the %p, %p, %p with all of the spaces, but that at the end here we can see that we have our address. What is still here though is this 20 value. That's because of this space here, and it doesn't exactly nicely align. So we need to make sure that we have it correctly. Okay, then we need to figure out where we are. So this is the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24th argument, if I counted correctly. So that means that I want to do percent. Actually, I need to do this percent. Oh no, I can just do it like this, percent, and then 24 is what I said, and then $, but I need to escape that because otherwise it's a variable, and then an S. Relish. Well, why is that? I have probably just printed something garbage because we don't align anymore. I've added 1, 2, 3, 4, 5 characters, and that means that I need to go to 38 because this was 3 characters, so that is -6, and then add an extra space, and then it should match. Not exactly. Apparently I've added some spaces again. No, that's also not correct yet. I don't think 24 is the correct value. Bingo. I've now counted the correct offset. Apparently I had an error. And you'll see that I'm printing this string here as part of my the memory that I dumped This is all from the formatting string, but you see here that we have the output that is caused by the %s, and that is now reading the global variable. And yeah, indeed, I was off by a thing with the printing. So yeah, this is demonstrating an arbitrary read. It's always a bit of a struggle to get that demo to work, but fortunately it worked out. But this is, again, still just reading strings, right? We cannot modify the program if we can only read things. Q%n. %n writes the number of characters that have been written so far. Why? I have no idea, but it writes it to the integer pointed to by the corresponding argument. That argument should be an integer pointer or a variant whose size matches the optionally supplied integer length modifier. That last part means using L or H or HH. Why? Just why do you need this? I have no clue. So much like the arbitrary read, we can use the arbitrary now %n to write data to an arbitrary place in memory. Again, we need the string being inputs being somewhere up the stack such that printf can read it, but then we can use %n to write it. We need to make sure that because %n writes into an int integer pointer, that we have this pointer to the place where we want to write. We can put an address in the place where printf will read the argument from, much like I just did with %s, and then we can control where we write. And writing something allows us to change variables, etc., or even override return addresses. And then %n will write the number of characters that have been written so far. Of course, if you want to write a full 48-bit return address, that is slightly impractical. You would have to write 16 terabytes of data. So what we'll do instead is we'll use length modifiers, and you could write it then in parts using %hn. We'll just write 16 bytes, or %hhn just 8. So demo time. Again, back to the Blinky program. If I want to now overwrite something, I could use %n. And I have a little bit broken the thing, but that's also because probably I'm somewhere halfway. So let's add a bit here. Oof. I've just broken my terminal. This is an interesting effect. I think I've just added a null byte or something. Yeah, of course, I'm writing a 8-byte value, or no, 4-byte value, and I've nowhere near written 4 bytes of stuff. So what I've just added is a null behind, because I was writing to 84, so that's 4 bytes into the string. And if you recall that the string started with this make it blinky character, I've overwritten the make it normal again character, and that one is gone. So now my shell is blinky. This is the type of things that the reset command should figure out for me. Yes. That was fun. Let's write something slightly more helpful, but then I have too many bytes again. So I need to 7, add 1 space, and then you see that I've overwritten one of the characters here into the string. Let's make it more halfway the string. And interestingly, Yeah, what is even happening? I think I overwrote the M character with something. 39. Yeah. 7. Oh, now I've underlined it. Well, that's all because I'm overwriting parts of these characters with, I have no idea what value exactly. 90. Now it's a secret string. It is easy to write over 1 byte, but unfortunately changing this entire string is slightly more complicated. I'll get to that in a second. This exploit is from the 1990s, so that's after C had been around for a very long time. And you can see here that Tim Tillman is breaking an FTP server just by listing this special directory. He's adding some bytes here, and then you'll see that he's writing a bunch of %use, probably to get this thing to point to the right place. And then he's formatting a special, no, this thing needs to point to the right place. Here he's using the zero fill functionality to just write a whole bunch more bytes, and then he's using %n. And what that did for him was that it made the return address point to these xxxxx's. And there he put the values of this thing. So that's 08074F DC was the address. And that would then give him a shell. This was an old exploit. As you might see, he's only writing 4 bytes. And why is that? On x86, addresses were 4 bytes exactly, which also meant that they didn't include null bytes, because in contrast, AMD64 addresses in user space are 6 bytes, but they're stored in 8 bytes, means that we always have 2 bytes that are null. And that makes it that much more annoying, because a null will terminate the string that we're writing. So exploits using these %n things or reading more than one thing with %s is a lot harder to pull off, because you need to make sure that if you want to overwrite the return address, you need to do that byte by byte. So you need to do 6, or if you're using doing it per 2 bytes, then you'll need 3 return addresses, 3 write operations, and does more than one address. And for a single byte, it's easy, but if you need to do more than one, then it's annoying, because you have these null bytes, and you can only get a null byte at the end of a string. So that means that you can only have the return address, a single one, at the end of the string. So that's harder. This is a good time to do the break, indeed. Yes, the rest is slightly more fun. So we will resume in 10 minutes. I will answer the question about needing to know Perl. The answer is no. I just find that this new one-liner that can print repeat the string very easily is convenient. I don't know any more Perl than that single one-liner. There's also ways to do that same thing with Python, but I am a bit more, that's a bit more typing, because you need to make sure that printf is being done correctly. You need to worry about brackets, etc. There's also a question about what this set arg does. So there is this feature called address space layout randomization. And that will randomize the addresses every time. So if I will do exit here, dash clear, then I have this terminal, printf.c. No, not a C program. You'll see that the address is different every time. And that is this Aslar feature. It makes the attack harder to pull off, because remember when I just did the attack with %s, of course it's gone, then I have a problem, because printf perl -e print you see that the address that's being printed here is different every time. It's different again, different again, different again. And that is very annoying, because in this attack that I just showed you, I was using the fact that this thing was constant, because I was printing it each time. And the way this program works is that you only get this information after having constructed this string. So you cannot construct that anymore after learning this information. So to do this attack, I need to turn off the address space layout randomization. And the -r thing is adder no randomize is the long version of it, and that disables randomization of the virtual address space, which is exactly what we wanted. So yeah, I will actually, and the reason why I want to run it with bash is that it will actually start a program that you give setarg with the switched off randomization. So if you start shell with switched off randomization, any programs you run in the shell will also have that. Will we work with attacks that don't depend on that? I'm not sure if we will talk about defeating Aslar, but I'm not sure if we'll get to that in the exercises, because it's slightly more complicated to pull off. You will need to reuse parts of the program against the program to do that. So yeah, I think that answers my question, the questions that I've gotten so far. I will now also take a small break myself, so see you in a bit. A bit being, what time is it actually? 5 minutes. I hope everyone managed to beat the queues at the coffee machine. So then we can start again. So buffer overflows is something we've mentioned a lot, briefly gone into, and in a more perfect world, they would of course not exist. If you run this in Python, we have the list that is 1, 2, 3, and you then try to get a 40-second element of it, you'll get a nice error telling you exactly where you are trying to access your list in an index that is not part of the list. Of course, checking the overhead of checking this and providing sensible errors to programmers is much too big. But again, remember the last time you spent hours and hours and hours debugging some segmentation error? Maybe your time is worth a bit more than the microsecond of computation that you save if you run a program without such checking. So if you ever face a decision that you need to choose what programming language you're going to use for a program, you'll need to think about if you really need C or C++, or if you can use a safer language like Rust or Go or Python, because clearly staring at segmentation error all day, which I've done before, is not pleasant. So, buffers on the stack. You declare a buffer. This is a character buffer. It's 20 long, and you'll quickly learn that reading the 20th value will work happily, but it is outside of this buffer. So what happens when we read this value? Well, we're reading up the stack. So the stack looks something like this thing here, and we'll be reading up it. And yeah, such bounce checking. If you don't do that, what can go wrong? The Heartbleed bug is probably the most famous bug. It was the first one with the logo, and it allows you to read memory that belongs to OpenSSL. And since SSL is a library that all it does is give crypto, it provides TLS. This contact typically includes cryptographic keys, password, very sensitive information. It was there for more than 3 years. It was introduced in 2010, but then they found it in 2014, and they made a logo, and they made T-shirts, and Peter Schwabe would be presenting this slide wearing a Heartbleed T-shirt. Fortunately, I don't have one, but yeah, major media coverage. In fact, this bug triggered a lot of re-engineering how such projects are funded. For example, the OpenSSL team was like 2 guys and a cat who did everything in their free time. They've gotten a bunch of money from, for example, the Dutch government to do things slightly more professionally, because a lot of people use OpenSSL. It is de facto TLS implementation, so it provides HTTPS to almost the entire world. And yeah, leaving that to 2 guys and their cat is a bit not ideal. The underlying problem was out-of-bounds array access. So XKCD made a super nice comic. Basically, the thing that you could do was you could send a request to the server, and you had to include how long the request was. In the example here, Megan asks potato, and this says potato is 6 letters long, and then the server will reply with potato. And the idea of this feature, which was an optional extension to TLS, is that it's a heartbeat. It allows you to send something over a connection that you don't want to send actual data over because you don't have that available at the moment or something. But then you make sure that the connection won't die because, for example, a firewall in the middle decides, oh, nothing is happening anymore, let's cut the line here. So then you could send these heartbeats, these echo requests over the wire to make sure that such applications like firewalls could tell that the connection was still active. The question here is what starts to happen once you do this. Reply hat 500 letters. Well, what would happen then is that OpenSSL would just read out everything that followed this buffer in memory. And in this example, you'll see that Eve administrator wants to set server's master key to 14835, etc. Problematic. Another example, ping. Ping is a protocol that lets you check if a server is online. You might have used it before. You can also use it to check what the round trip latency is. So then if you might be familiar with ping in video games, and then people hiding their bad skills at Counter-Strike by complaining that they have too much ping. Ping is about when you send something to the server and the server immediately will reply, how long does it take for that reply to get to you? So you use that using ICMP, and then the server will send the same thing back. You'll see here that I've pinged my VPN host, and it replies within 15.4 milliseconds, 15.10 milliseconds, etc. It's sending some number of bytes. The payload is 56 bytes, but then there's a bunch of header, I think. Yeah, very nice to debug your network. So IP packets have a limit in size. They can be at most 65,535 bytes long. And if you want to send something that's bigger than that, you can chop them into these fragments for transportation. Each header then has you can put them together, and then you say this is a chunked packet. So you send, okay, this is the chunk that starts at 0, and then 0 through 100, and then the second packet says I'm starting at 100 and I have the rest of the data, etc. This fragment offset plus the packet size may still not exceed this limit. This limit is if your transport that you're sending the packets through is more narrow than what can be the size of a packet. Of course, we can still forge such a packet though. So this led to the ping of death attack. So what you would have is that the host that receives a ping packet would assemble these fragments in a buffer, and the buffer would have a constant size saying, okay, I'm 65,535 bytes long, because everyone just assumed, oh, it can never be bigger than that. But then they wouldn't check if you set a fragment offset that was too big, and then also the size of your packet was too big. And it was so bad that with some implementations, you could just send this packet saying, ping, I want a payload that's this big, and then to the target, and then it might even crash. Lessons. Assume anything you get outside your program is broken. Anything. Also, assume that the specification will not help you. And specifically for this ping, check if the fragment offset plus the size of the packet that you're getting is below the threshold. IPv6 was introduced as a follow-up to IPv4 in the late 90s already. Many people still don't have it, but that's a separate discussion for Paul in network security. In the late 90s, early 2020s, IPv6 was introduced everywhere. All of the devices usually support it, but yeah. You see where this is going. So in 2013, another ping of death attack was found against Vista, many versions of Windows. In 2016, a bunch of routers, very expensive hardware from Cisco was broken. Yeah, again, people assume things from the standard and they don't pay attention, and then someone uses something, yeah, against you. So why does this work? Why does this work in the first place? So we have the C specification that has these description of things, how they should behave. But like we said in the first lecture, we have some things that are undefined, and there anything may happen. Undefined behavior for which the standard imposes no requirement. Permissible undefined behavior ranges from ignoring the situation completely within the predictable results to having demons fly out of your nose. The reason why this is there is that it enables some assumptions that allow your compiler to do smart things. But strictly speaking, you could get that by giving an error upon compilation if you have something that is bad. So yeah, the examples, division by zero. This is a fun one, modifying between sequence points. So what you have here is that I++ increments I, but it first returns the value. So in this line, it is very hard to say what you should set I to. Should you set it to I plus 1 plus 2, or should you set it to I plus 1 and then store it, and then this plus plus happens? What is the order that makes sense there? Instead, that's just not allowed. Null pointer dereferencing, using uninitialized variables, indexing out of bounds. And another fun one is signed integer overflow. So compilers may assume that this x, which is a signed integer, will never be smaller, will always be smaller than int max. No, sorry. In this piece of code, we have that we set x to integer maximum, and we have that we then add something to it. So if you ignore all of the sizes about integers, we will remove this line. Because the compiler sees x, oh yeah, that was int max plus something. Well, something is a unsigned number, so it has to be positive, so it's always going to be larger than int max, and removes that line. But then what will happen is that you will probably roll over to the very negative, and yeah, mess happens. I should say that for unsigned integer, overflow is defined, and there you just will roll over back to 0. Why does this go wrong? Well, users. Unfortunately, we have to expose the nice software that we wrote to those people who will always find some way to break it, namely the users. Remember when your mom had those 20 browser toolbars? Exactly. So this very frustrated programmer was very fed up at some point, and insisted that the user please go somewhere else and don't bother me with your bad behavior anymore. Please purchase from my competitor. Here, pepcarc means problem exists between keyboard and chair. Users, the problem is that you have all sorts of assumptions in your head while you're writing a program, and the users are either not aware of that, or they are maliciously not respecting those assumptions because they are approaching things from another aspect, maybe not from a technical aspect, maybe from a very technical aspect when they try to hack something. But they will look at these assumptions and then just stamp all over them. And there is a lot of software exposed to a lot of people. If something is on the internet, that means that in principle 4.5 billion people can access it. User input goes into your program because usually your program doesn't do anything without getting useful input. But it could get there in many different ways, even ways that you don't think about as user input. So you could get keystrokes from the keyboard, that's very obvious, or network packets when I send a GET request to a web server. But other forms of user input are files, because I can modify a file that's on the storage, and then it can be read by the program. There comes the fire department. Yeah, and then it will be read by your program, and if the assumptions that you have on how your file looks like have then been changed, then you could break your program. Database content is another good one. Often there it goes wrong because you took user input at some point in the past, you stored it in your database, and while you were doing all of that, then you were very, very careful, because that was user input. It came directly from the user and it was very scary. And then you read it from the database again, and you forget to check all of that again. And then through the database, this user input still comes to bite you in the butt. Another very fun way of user input is the name of your program. So I have here the program called printf file name .c. It's very simple, it prints the argv0 argument. But what if I do that? Works, and that also works. And in this example, I've compiled it, but I could also create a symlink to %x called %peep, 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 %peep. And then you'll see that it's printing more information. It's getting the name of the program at runtime, and because I can create aliases for programs, this is also an attack that anyone can do at any time. Very fun ways in which assumptions can often be broken, even the ones that you didn't know you were assuming, such that the name of the program is something that is very static. How do we fix this? Well, memory safe languages are a very good option. In those languages, if you go out of bounds on your memory, if you do memory unsafe operations, they will stop you, tell you you're doing something wrong in this place, and you will usually then terminate, or sometimes you can recover from it. Java, for example, null pointer exception, etc. If you do have to use an unsafe language, make sure to turn on at least every warning that you can. The compiler has a lot of features that it can help you with, but often it won't if you don't tell it to give you those warnings. So WAL, WExtra for extra warnings, because why aren't those enabled by default? Pedantic tells you when you're doing non-standard things. WFormat and format security help find the problem that we just saw. So if I go back to here and try to compile this with clear W4, it tells me that the argument for printf is not a string literal and no format arguments have been given, so that it will start printing the wrong thing. There's also everything on Clang, but that's not often very useful. There's also something as too much warnings, and if you turn on W everything, you also get all of the experimental stuff that's there and not always useful. Another way to find such problems is to run with sanitizers. So a sanitizer equals address will try to figure out if you're doing all sorts of accesses into memory that are illegal, similarly for undefined behavior. And these are dynamic analysis tools like Valgrind that run at runtime. They slow your program down, but that's because they are checking everything in the backend. You would use these while testing and then turn them off while when you ship the end product to your users. That's dynamic analysis, but there's also then still the tools that are called static analysis tools, and those try to analyze your code at compile time, and there's a bunch of very advanced ones that try to find also all sorts of bugs. So yeah, inserting our own code. Time. Yeah. So we have this buffer and we want to inspect it with printf. So how does this work? Well, we have the buffer and it writes all of these. It's 20 characters long. We start at A and then add A plus the integer for each position. So we get A, B, C, D, E, F, etc. until T. We call that function from the main function and we supply the first argument. That program we can very easily make because it's here. And buffer send peep, send peep, send peep, send peep. Oh. And you can see here that I should print some. Send peep, send peep, send peep, send peep, send peep, send peep, send peep. And you see that we here see some string appearing. 48, 47, 46, 45, that's clearly these values. But then if we read past that, let me add spaces. Excuse me. You'll see that we can start seeing other things appear. So there's a good chance that this is the frame pointer, and this is the return address as we read up the stack. Slides. So that's reading with reading up the stack. We've seen that before. We have done that a bunch of time with printf. And reading is fine. It helps us learn things. But what about buffer overflows? So this is the getS function, or at least the manual page from the getS function. It has a bunch of very, very fun sentences in here. Deprecated. Never use this function. And no check for buffer overflow is performed. See bugs. Never use getS because it's impossible to tell in advance how many characters it will read, and because it will store characters past the end of the buffer, it is extremely dangerous to use. It has been used to break computer security. Use fgetS instead. Fun. So how does this work? Let's look at this function. So we have a nice buffer here. We have here printf, which asks us to enter our name, and then we call getS to read the string. Then we will print that string back at the user. Our main function in this example doesn't do anything except calling func. We don't get arguments. We are reading the input here from the user. So if you compile this, we will get a fun warning. The getS function is dangerous and should not be used. I can also do that here. What was this program again? Bufferville. In function func, getDes is dangerous and should not be used. It also tells here that it's deprecated and very scary and stuff like that. I can also run this program, bufferville. Please enter your name. I am Tom. Your input was Tom. Tom, %p, 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 and you'll see that we have the familiar printf vulnerability. I will now use input redirection to give this program some input. I do echo and then I use this pipe. This is the vertical line character, and then into bufferville. You'll see that that's an easier way to give input to this program. So I will now use a trick that allows me to do more than one thing. I'm going to need to use -n here, otherwise put a new line. You'll see that this allows me to concatenate the output of more than one command. So let's make this the Perl thing that we've been using before. And I hear the fire department coming again. And I want a space. Ah, it's already crashing. Let's do slightly less things here. You'll see that we can print the entire buffer again. I would not hope that they are coming here because of the use of getS, because I'm not sure. Oh shit, they're turning into my street now. You jinxed it. Okay, they're going on further. Yes, we are overwriting the buffer with all sorts of our formatting characters, and yeah. Interestingly, we see some address here, but that's probably something left over by a different function call. So what happens if we overwrite this? Well, we start reading into this function. So what starts to happen if we start feeding this 116 A's? Well, we'll first write all of the 100 A's that are fitting in the buffer, and then we'll start to overwrite the frame pointer. And then we're starting to overwrite the return address, and then our program will crash. You can also see that in the example. We'll just do it with a single line here. 116. Oh. And then we have that 116 still works. What about 24? It's hanging on. Well, 300 definitely isn't too much. 200 minus. In my example, I had 200, so that's 216. Illegal instruction core dumped. Why do we see illegal instruction? Apparently, we jumped to memory that was still legal to jump to, but it resulted in a crash. I'm going to store this string to input. So let's try to figure out what was going on. So I'll use the debugger. Break on, what's the function called again? Well, I think. func. I want to break on function. And I want to run, and I want to give this thing input. Yes, I want to start from the beginning. You'll see that it's now in the buffer vuln function. That was not what I wanted to do. I always forget what these things are. So if I do next, it's to start reading the input. And then let's first, before we do that, look at the stack frame. So we have here the saved instruction pointer, and we have the frame pointer, previous frames stack pointer is this thing. But if we now start to read those way too many characters, you can see that we've overwritten part of the instruction pointer. And I expected here to see more A's, but apparently not. The return address has been overwritten partially by a bunch of zeros. And why is this problematic? Well, it's now jumping to some other place that's still part of our code, but not properly aligned. So if I will now do next, 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 and then now it's returning. It's doing some detours. Well, eventually it'll end in illegal instruction. And we're getting illegal instruction instead of just segmentation fault because it's still part of our program, but it was not a valid place to jump back to in our program. So I tried to run something that it didn't understand, and then it says illegal instruction. Back to the slides. So that happens if you give it a bunch of A's. But what if we start to feed it slightly more interesting data? Oops. So this type of overflow allows us to take control of the return address. If we overflow the program with an address that we know, that we know does the thing that we want, we can get this program to return to code that we want to return to, and not to the normal place where it would return to. So we can use this to execute our own code, which we're going to do next week. So please give me the next slide. Yes. Note that I'm giving the address here in the reverse order because, again, endianness. So the last byte will be the most important one, which means that you need to give it in the right order. The actual values here will vary with alignment, buffer sizes, other local variables, etc. So you need to figure out, usually the idea is that you first figure out when does my program crash exactly, and then you'll try to overwrite your return address. Using GDB to do so is very helpful. In this week's homework, you also need to be using GDB. I unfortunately don't really have time to film a tutorial for GDB, and I think other people have done very nice tutorials already. We link to one of those in the assignment, but you can also use any tutorial that you want. So homework. This week's homework is a simple buffer overflow where you need to corrupt some memory, and it is so easy that a child can do it because it gives you a lot of feedback while you're doing it. The other one is finding a vulnerability using GDB and then exploiting that vulnerability. Use the links and follow a tutorial, very important. And finally, you want to redirect a program to call a function that it shouldn't have called. This is slightly more advanced than what I've shown you so far, but I think it's a lot like the first one, the first exercise that you've done. And I think also definitely once you see the lecture of next week, I will go into that type of attack in detail. So then you should be able to do it quite quickly after that lecture, but I think that a lot of people will be able to figure that out already, that one. The last week's homework. So I understand that magic function is a hard exercise in the sense that it's slightly tricky to think about what's going on, but it really helps to draw some pictures of magic function. If you are getting sizes that are way too small, much smaller than you're expecting, you probably need to make sure that you use the variables that you're defining. For example, try printing the results, looping over an array. You could try to mark a buffer as volatile. Those are all sorts of things that you could do to allow the magic function to not be compiled away. We are not looking for exact answers there because we also realize that there's differences between compilers, etc., and the various strategies that you can use to attack this function are tricky, but we hope that you can think about it. I will now try to draw a bunch of pictures. This amazing website allows me to draw things on my tablet and then show them to you on my screen, but it's not super amazing, so bear with me. I need to make some space for my keyboard. So what happens when we call a function is that it allocates space on the stack. So imagine that we're in function, and then this function calls a magic function. And that uses some amount of stack. And it makes a mess of that stack by changing all sorts of values there. And then once it's done, you return, and then you will go back to this situation. But what's actually happening then is that the mess that magic function made is still there. And that's something that we can use to exploit this. Imagine, for example, that you somehow try to prepare this piece of stack. And then once you run magic function, you'll start to see where it has made stuff messy. And then you can try to see where it has changed things and where you can find your green stuff again. And then doing that, you can try to figure out what you're doing. And I saw that, and please don't do this. I cannot kick people. But I think that was enough for the explanation, and otherwise blame your fellow students. So really draw these pictures about what's going on, and don't be afraid to go into some undefined behavior, as were the hints already telling you to do. I've really tried to give you as much help as possible on that thing, also in the text of the explanation. Yeah. Some people have been complaining about crashes. This is again this week's homework. Exercise 2, the one with malloc, should not crash. If you find that that is crashing, you are maybe not checking if something is null, trying to free a null, accessing memory that is not valid. But in principle, you should be able to call malloc until it will return null. And if you are thinking, but then I will need to do that a gazillion million times, have you ever heard about binary search? And with that, I think I've given enough away about exercise 2. If you run exercise 4 and it does crash, that is intended that exercise is leaking memory. So please don't send me emails about that. And with that, I would like to wrap up this lecture. But I also still want to explain the exercise of last week. So unfortunately, I don't have a lot of time to do that tomorrow, so I want to do that today. Let me briefly set that up. So this was the first exercise where you needed to print all of these things with alignment, and not with alignment, and learn that it was not always in the same order, etc., because alignment would make it nicer to put it in a different order. I will need to find where I put the write-up of this thing. So we have this program again, here with some more color. And if we want to print it, I have the solution here. Well, this is a bit of a mess. You can just add a bunch of things that do printf address. So that's a %p, and then top, and then I need a variable, which is a %d in the first example, and then a value, which is another. No, the variable is just a, and the value, and then another top, and then the size of, and then another top, and then the next address. And that's also one of these, and the new line. And I wanted to then print the address, so that's and a. Well, a is just the thing that's encoded here. The value is just a, size of, and the next address. Well, that one is, as we know by now, just this plus 1. And if you then do that for everything, then you get something like size of solution.c, where this is using some nicer formatters, but does that for every single line. What you then get is size of solution is a table that looks something like this, which will print all of the variables and all of the addresses. And if you use sort, you'll see that you'll get a different order, but it's nicer to do sort reverse. Reverse, yes, the other one was random, because then we get everything nicely in order. And you see that I should use this one. Yeah, sorry, this one is nicer. You'll see that everything here is nicely consecutively in this example, except here, you'll see that this goes to 800, but then the next value is found at 802 instead of at 800, and that is because of alignment. In the second exercise, you needed to do this with the bool. Well, it was quite easy that everything that is not 0 is true-ish. So you could write this short program that basically prints that everything is true except 0. The tuplement program is a fun one. I said that it was a exam question in previous years, and what you needed to do is write a program that prints this computer uses two-complement representation if that is the case. toComp.c int main, because we're not going to need more. So imagine we have an int called a, and it's the value 42. If minus a equals the bit flip of a plus 1, printf this computer uses to complement notation. Else puts nope. And indeed, that is correct. And why is this correct? Well, it boils down to how toComplement is implemented. What the squiggly line does is it flips all of the bits of the number. It just immediately bit flips them. It doesn't care if it's an integer or not, it just flips all of the bits. Well, it does care if it's an integer or not, but it's a bitwise operation that's defined over the bits and not over the numerical representation. Minus a does a numerical inversion. So what that will do is it will go to complement notation negative. Now, in the slides, I said that toComplement is flipping the bits and adding 1. So that is exactly what I'm doing here. Then I check if that is the same as numerically inverting a. And since it is equal, we see that this computer is indeed using toComplement notation. And then in this exercise, you needed to mess with pointers. I hope that I can copy this. Oh, that shouldn't have been Vim. Cut pointers, let's see. And then what you could do here is that for our pointer e is I was setting up the exercise from the text of the exercise, so you've not missed much yet. But now I'm starting to print all of these things. So what I'm just doing is, X is also already taken, A. And I'm just going to start from the address of I. Now actually let me start with something else. Slightly nicer. I. What did I need to print again? I need to print the address, the content, and so I need to do pointer, the content in X, to X, and I want to do it as a byte, and I want to print the content as decimal, and D. And that means that I need to do I pointer plus Z, I pointer plus Z, and dereference I pointer plus Z. What I'm doing here is I've missed a, there we go. I'm just taking the pointer and adding Z to it, so I will print starting from I and then the next 20 bytes in memory. That might not prove enough, but it's a good start. Make pointers. Sure. And then you can see that we get a bunch of deep bytes in memory. HH, make sure that we print it as a byte, because it's a half and then the half again of an integer, because the D will expect an integer. So what are we seeing here? Well, I see a 1, 2, 3, 4, some 2, some other values that don't immediately make sense. Let's add this, change this to the next 50 bytes. And again, okay, also expect to see 1, 1, 2, 2, 3, 3, 4, 4, etc. I see a 1, 1, 2, 2, 3, 4, 4 here twice. Interestingly, in 2 directions, so that's again because of endianness. I don't really see where my student number is. But yeah, that's more or less what you should have done to print it. Possibly it reordered things such that my student number is below a thing. You could have figured that out with a bit more time. And compiling it with the extra options as asked in the C part of this exercise might have revealed that some order gets changed. And then the add vector exercise was quite straightforwardly changing this by R plus I and then a star in front of it. So doing terminal. We had, let me cheat and look at the thing. Void add vector in pointer R const equals 0 is less than the length of the input. I will just do I plus plus. Ri equals ai plus bi. So this was the example that was given, and then we needed to change this into pointer arithmetic. Well, that is easy. We just do this. And then we can do everything with pointer indexing. Writing a memory comparison function was more or less doing the same. Int memcomp. You need to get a uint8 unsigned. No, I think it gets a char. Character pointer A, character pointer B, size t len. And now we're complaining about not returning anything and missing size t. And that it already exists. So what we'll do is just for e equals 0, I less than len I plus plus, if a plus I not equals yes, if a plus I not equals b plus I, return a minus b. And if you want to do this correctly, you should have taken the sign. Although I think that it needs math.h. Or you just test if it's messy. If then you return -1, else return 1, and this should be a valid version of memcopy. This can be done neater, and it can be done quicker, and it can be done more efficiently, but it's more or less the same thing. The backwards function is simply starting from the back, so then you start with len -1 and is greater than or equals to 0 and I minus. And then there were the optional versions. So for the fast one, then you can need to make sure that you keep this around for the remainder and do something like memcopy returns 1 if the result is not equal, it returns 0 if the result is equal. If you wanted to do the faster version, you would have to do something like this is and the same for B, and then you would do for equals 0 until I is greater than len divided by 8, because now we're doing it by 8 bytes. Let me change this into the and then you would do this comparison. And because we're now comparing, we need to do the long versions here. And now we're doing it by 8 bytes. And then there is only the remainder here. I need to take this out of this loop. Let's do this nicely. J. Because I took it out of the loop. Oh, I now need to change this to J. Let's do this I still. Change this to J. Starts from I times 8 until it's greater than, well, it needs to be smaller, of course. j and j plus, and then j, and then j. What we're now doing is, in the first part, you compare 8 bytes at the same time, because we're comparing long longs, which are 8 bytes. But then if the number is not nicely divisible by 8, then we have a remainder. So I make sure that I start at that remainder and then do the rest that remains. For the, this is the fast version. We should do this fast. And then for fun, there's the constant time version, which is more or less carp A. Oh, that's off the screen on your end. Difference is 0. And then until len, if difference is -1, differ is 1, and this will always take the same amount of time. Although actually this is still attackable, because you can tell if you would try to attack this piece of code if you take this branch or this branch, probably. But I have no time or interest to do all sorts of weird bit arithmetic to solve that even further than this. This would have already been sufficient for the purposes of the exercise. So that is that. I am going to upload this explanation as a separate video from the lecture once I get YouTube to finish processing everything. But I think that for now, this is it for this week. Unless there are any more questions, let me quickly peek at the chat. There was a question about return addresses, if they have to be on the stack. The return address that you are overwriting is on the stack. So the address where you're trying to jump to is not on the stack. That's part of the code segment of your program usually. Or maybe indeed it is on the stack, but the it doesn't really it doesn't matter where what the address is that you overwrite with, where that is. But remember that the return address itself is on the stack because it is a stack variable. And with that, I think I'll end for this week. I will see you again later, and have a nice evening.